record. Okay. So let me show you change the camera. Here we are. All right. So this is a copula. So a copula is a function that used to describe the dependence between two variables x and y. For example, you could have x equal to oil price and car price. Obviously, these are dependent. And the same thing here, oil price, food price. A copula is, in the two variable case, is a function from 0, 1, comma times 0, 1, which is a square, into the unit interval 0, 1, right? So that's when you have two variables, with the conditions that c at u comma 1 is equal to u, and c at 1 comma v is equal to v. And these two conditions tell you that the marginal CDFs of c, which is this, are uniform 0, 1. Right? That's what these two conditions tell you. All right. Okay. I hope you guys looked at the videos I asked you to look at. There are. Okay. Suppose you have a random vector x comma y with this as the joint CDF and this as the marginal CDF of x and the marginal CDF of y. There are two statements I would like to discuss right now. The first statement is that for every joint CDF of x and y, there is a corresponding copula, and this is the proof. This is the proof of that statement, that for every joint distribution of two variables x and y, there is a corresponding copula, and the proof is given by this. I'm not going to go through this proof, and I'm sure you maybe looked at it already. And if you don't follow the proof, you know what to do. Just contact me, okay? And there's a second statement which says the following: that for every copula C, there is a corresponding joint distribution of x of two variables x and y, and the proof of that is given by this, right? And again, if you don't follow this proof, please contact me anytime, 24/7. I'm sure you know how to contact me by phone or by email or by any means, you know. All right, and there are two simple copulas. The first copula is known as the independent scopula, for which the capital C at u comma v takes the formula u times v, and it can be shown by some simple math. If you follow this argument, I'm not going to go through this again. If you follow these arguments, that you can show that this statement, that the copula u comma v is equal to u times v is equivalent to this statement here, that the joint CDF of two random variables x and y is the product of the marginal CDF. And you may remember from your courses that you've taken in the first or second years that this is the usual definition of independence of two random variables x and y. So basically this copula here corresponds to the usual definition of independence, right? That's the first of the two simple copulas. The second of the two simple copulas is known as the complete or completely dependent copula, and for which the capital C at u comma v is defined as the minimum of u comma v. And again, if you follow these arguments, I'm not going to go through them step by step. I'm sure you guys are good enough to follow this argument by yourself. It can be shown that this statement is equivalent to this statement here. That is, the joint CDF of x and y is equal to the minimum of the marginal CDF of x and the marginal CDF of y. And this, if you don't know this already, this is the usual definition of complete dependence of two random variables x and y. I mean, you say that two variables x and y are completely dependent if and only if the joint CDF is equal to the minimum of the two marginal CDFs, right? So again, I have shown that this copula here corresponds to the usual definition of complete dependence of two variables, right? All right, so that's it. All right, now we come to the formal definition of a copula. A formal definition is the following, that a function from this is the square, unit square, that is 0, 1 cross 0, 1 to the unit interval, is a copula if it satisfies these 6 conditions. So the first condition is that c at u comma 0 is 0 for all u, c at 0 comma v is 0 for all v, c at u comma 1 is equal to u for all u, c at 1 comma v equal to v for all v. The partial derivative with respect to u is non-negative for all u and v, and the partial derivative with respect to v is non-negative for all u and v. So if these 6 conditions are satisfied, then a function from this to this is said to be a copula. All right, I will do a lot of examples later on today and also on Thursday later this week. All right, so don't worry about it. Okay, and this is one example. I'm not going to go through this now. This is one example I did in the video, which you have already watched the video. This is the second example I did in the video, which you have watched it. And this is the third example I did in the video, if you have watched it. Okay, right. I mean, once again, if you have questions on the examples, just please feel free to contact me, right? Okay, now to the 2 most popular models for copula. The first one is known as the normal copula, or also known as the Gaussian copula, and is defined by this formula here, where phi, I'm sure you guys know, is the CDF of the standard normal distribution, right? By the way, are you able to read this, guys, or is it not focused enough? Let me know if it's not focused. I'll try to focus it better. You guys okay, guys? Yeah? So if it's not focused, just please let me know, okay? So capital phi is the CDF of the standard normal. Capital phi 2 is the joint CDF of the standard bivariate normal, right? So this is the joint CDF of the standard bivariate normal. And this is the normal copula, or the Gaussian copula, all right? And it is the most popular, it has been the most popular copula up until 2008. The reason I'm saying this is because, I don't know why it's not focused properly, I'm not sure. Maybe, let me try to focus it. Excuse me, guys. Sorry, guys, sorry. I think there's something going wrong. It's not, there's something wrong here. Just a minute, just bear with me. Oh, shit. Excuse me. Okay, now hopefully you can see it better now. I don't know. Hopefully you can see it better now. Okay, now this copula here, the one I mentioned over here, has been the most popular copula up until 2008. The reason for that is because you may recall, I think I mentioned this before in this course, that in 2008 or 2009 there was a big financial crisis, right? And a lot of people lost a lot of money across the world, basically, right? And one of the reasons that they lost the money is because the people, like, for example, the people in Wall Street, for example. I mean, you think the people, I mean, you think the people working in Wall Street are probably the most brilliant people in the world, but they are not. They have been using the normal copula, or the Gaussian copula, to model portfolio losses. So they've been using this formula to model the portfolio losses. But the problem is that the financial data it do not actually follow the normal distribution well. I think it's a well-known fact that normal distribution does not fit financial, like stock data, for example. Stock data doesn't fit the normal distribution well, right? So you should try to use this. You should try to use this to describe the dependence between two different stocks, for example. It will not give a good fit. Right? But people in Wall Street, and the people, I mean, like places like Wall Street, I mean, which you think is one of the top places to work in the world, right? I mean, they've been using the Gaussian copula for everything. That means it did not, without even realizing that it did not give a good fit to financial data, right? So since 2008, people chose not to use the Gaussian copula or the normal copula because they realized at that point that the use of the Gaussian copula to model stock data or dependence between stock data might have led to the crisis in 2008. Right, that's when this, I don't know whether you guys read this paper. There was a paper written by an American statistician. He's also a journalist. I mean, this the name of the paper is called "The Formula That Killed Wall Street." Right. This is I actually put a copy of this paper on the video. I don't know whether you guys saw the video. This basically, when they say the formula that killed the Wall Street, they actually refer to this formula here. They refer to this formula as the formula that killed the Wall Street, right? Okay, and and you should read the paper. Maybe you can read the paper when you have time, guys. I will show you. Yeah, I don't know whether you can see this. I think it's kind of blurred. You may not be able to see it correctly, but this is actually, this formula here is the formula that I just wrote down. This formula here in the paper is the formula that I just wrote down, which is this one here. Right? These two are the same. So they refer to this as the formula that killed the Wall Street because it didn't give a good fit to the dependence between stocks, for example, right? So since 2008, people have been trying to find better models for copulas to describe the dependence between stocks, for example. So one of the models is the following. I'll show you in a minute. It's one of the models is known as the T copula. The T copula is defined by this formula here, right? This is the formula where TA is this one, right? Is the CDF of the student's T distribution with a degree of freedom, right? And capital T2 is given by this formula here, and that's the joint CDF of a bivariate T distribution with a degree of freedom. And it has been shown that this copula, it has been shown that this copula is a much better model for stock data, financial data, than the Gaussian copula, which gave a really bad fit. And it might have been one of the reasons to lead to the 2008 financial crisis, right? So since 2008, one of the models that people have tried to use, especially in the financial sector, is the T copula, which is given by this formula, right? Okay. All right. So I just wanted to talk about these two models, the Gaussian copula and the T copula. But there are many other. I mean, there are many other models for copulas you can find in the literature. I mean, if you're interested in other models for copulas, you can actually see them on the course webpage. I will show you in a second, right? So these are just two of the copulas that I wanted to talk about. Okay. So let me change the camera just a minute. Let me go back to the. All right, here we are. Share screen. Here. Okay. So if you go to this is the course webpage, as you know. So there is I have put like course. Here we are. I think maybe this one here. I don't know. I'm trying to say you should look at the supplementary notes, right, which is printed notes. Not this one now. No, not this one. No. I'm trying to find the notes on the copulas, guys. Just give me a sec. Oh yeah, this is the one. So this, so if you look at this, which is chapter 20, this is long, and it gives you a collection of different copulas that can be used, for example, to model financial data. So as you can see, there are many different types of copulas. Some of these are named after people who invented. Like, for example, this is named after these two guys, this copula here, and so on, right? Okay, so I mean, this is just for your own curiosity, but you don't need to know this for this course. I'm just giving you this information just to just to satisfy your curiosity. So there are like, I mean, more than 100 different copulas in this chapter if you want to look at it when you have time, right? Okay, all right, guys. Let me go back to this. All right. Now, what I'm going to do in the rest of this session today is I'm going to do some examples on copulas. All right. Sorry, what am I doing? Sorry. So let me go back to the camera. All right, here we are. Okay. So the first example, all right, is the same as one of the examples I did in the video. So you might have already seen this, I don't know. So example 1. All right, is to show that this is basically the independent scopula, right? So we want to show that it's a copula. So remember, to show that something is a copula, you need to prove 6 different things, right? All right. So the first thing you need to show is that C which is U1 times 0 is equal to 0 for all U1. So this condition is satisfied. The second thing you need to show is that C all right, is also satisfied. And the third condition you need to show is that C all right, so it is satisfied. Okay, guys. And the fourth condition you need to show is that C yeah, so this is satisfied too, right? And the fifth condition you need to show is that the partial derivative with respect to U1 of this, right? So you should take the partial derivative of this with respect to U1, you will get u2, which is clearly greater than equal to 0, right? Because remember, each of these is between 0 and 1. Remember, because as I said before, the copula is defined from the unit square to the unit interval. So that means each of these guys is a number between 0 and 1, right? Okay. So this condition is satisfied too. And finally, condition 6 is all right, so this is the partial derivative with respect to u2. So this is u1 greater than or equal to 0. So this condition is satisfied. So all 6 conditions are satisfied. So hence, right, hence is a copula. All right, you guys okay with this example? This is a very simple example. I mean, I made it so simple, but I mean, you may not get such simple examples in the exam. So, by the way, the exam, I send you guys details about the exams. I think it was before the new year. I think did you get my email, guys? I send you details about the exams. It will be 3 hours long, and after 3 hours, you will have. I think it will be from 9 to noon. So after that, you will get like 1 hour or so to upload your answers to Blackboard, all right? And then I will start marking. Okay. So if you have, I mean, if you go to the website, there are many, not well, there are past exam papers and solutions for the last 7 years. So there should be plenty for you to practice on. So I mean, I have solutions and exam papers for the past 7 years, so it should be enough for you guys to practice, right? But if you need, of course, if you need help, I mean, you can contact me so 24/7. Okay. All right. So this is example 1. Example 2. Um, right. Okay, guys. So we want to show that this is a copula. So this is slightly less straightforward. So the first thing you need to check is whether C at U1, 0 is right. So if you put this is what you get. Now 0 to the power negative 0 raised to negative power is infinity, right? So what you have is right infinity. So infinity plus anything is infinity. So you get this to be equal to 0. right? Because infinity to the negative power is 0, right? So this condition is satisfied, right? Okay. Once again, this guy is infinity. All right, and infinity power negative power is 0. Right. All right. The next part is C. Okay. So this is gonna be right. Now this is 1 minus 1 is 0. So this will be equal to U1. So this condition is satisfied. Okay. Condition 4. Okay. Now this is 1. 1 minus 1 is 0. So this power minus this power, this one is U2. So that condition is satisfied too. Right? You guys with me so far? Let me know if you have questions, all right? Just don't be silent, all right? If anything not clear, please let me know. And condition 5 is the partial derivative with respect to U1. Right? So if you take the partial derivative with respect to U1, it will be, I'm sure you guys are experts, so you probably know better than I do about differentiation. So this is minus 1 over alpha, right? Then yeah, okay. And then multiplied by minus alpha times U1 minus alpha minus 1, right? Now these two cancel out. So what you get is the following. You get yeah, and then because these two cancel out, so you're left only with this term here, right? So you get U1 yeah, and clearly, I mean clearly this is non-negative, this is non-negative, so this is satisfied. Okay. All right. So condition 4. So condition 5 is satisfied. Right. So next, the next condition we need to check is condition 6. Condition 6. So you take the partial derivative with respect to u2. All right, and you should do that where you will get minus 1 over alpha multiplied by and then minus 1, minus 1 over alpha, then you multiply by minus alpha u2 minus alpha minus 1, right? So once again, these two guys cancel out. So what you have is this, right? And this is clearly non-negative, right? So all 6 conditions are satisfied. So hence, right? Okay. All right. So this is this okay, guys? So any questions on this example? Hello, guys. Talk to me, please. Okay. Thank you. All right. The next example. The next example I'm gonna do is the following. So let me take this away. This is example 3. All right. Okay, so here we have a minimum of u1 and u2 power theta, and then multiplied by u1, u2 times power 1 minus theta. All right, so the first condition we need to check is this, right? And this will be minimum of u1 comma 0 to the power theta, then u1 times 0 power 1 minus theta. So this is 0, this is 0, so the whole thing will be 0, right? So condition 1 is satisfied. Condition 2, all right, again, this is 0, this is 0, so everything is 0, all right? Condition 3, All right. Right. Okay, u1 comma 1, then u1 times 1 to the power 1 minus theta. Now the minimum of these two is clearly u1, right? Because remember, u1 and u2 both, they are both numbers between 0 and 1. So the minimum of these two is u1 power theta, and here you have u1 power 1 minus theta. So this is u1. So condition 3 is satisfied. And condition 4 is like this, okay? So here, once again, the minimum of these two is u2. And here you have u2 power 1 minus theta. So this is u2. So condition 4 is satisfied. Okay. Now condition 5 is the partial derivative of okay. All right. To find the partial derivative, you have to be a little careful here because the copula is defined differently depending on whether u1 is the minimum or u2 is the minimum, right? So you have to separate out the two cases. So basically what you need to do is the following. You need to say like this, right? Now if u1 is the minimum, right? So if u1 is smaller than u2, right? Then you have this if u1 is less than u2, right? This is what you will get, right? On the other hand, if u1 is greater than u2, then you will get yes, if u1 is greater than or equal to u2. This is what you have, right? All right. So because otherwise you can't take the derivative without actually separating the two cases, right? Okay. Now you can take the derivative inside the two cases. So if you differentiate this with respect to u1 and this with respect to u1, you will get you will get the following. You will get let me show you, right? So if you differentiate this with respect to u1, you will get u2 power 1 minus theta, right? Yeah. Now, if you differentiate this with respect to u1, you will get 1 minus theta times u1 minus theta times u2. Right? And both these numbers, this one and this one, are both non-negative because remember theta, as I said before, theta is a number between 0 and 1. So this is non-negative and this is non-negative. So both are non-negative. So condition 5 is satisfied. Okay, so this is how you will do it. Okay, and finally condition 6 Excuse me. Let me do condition 6 now. Condition 6. Here we're going to take the partial derivative with respect to u2, right? So this is going to be the partial derivative. Once again, you need to separate out the two cases, right? So the first case is where this is the first case, and the second case is right. Okay, now if you take the derivative inside, you will get the following. You will get the derivative of this with respect to u2, right, is gonna be this. Yeah, that's if and the derivative of this with respect to u2 will be u1 . Okay, so both this, clearly this is non-negative and this is non-negative too, so this is greater than or equal to 0. So the conclusion is that hence right. Okay guys, are you okay with this example? No. All right, so this is example 3. Maybe I don't know. Well, this is example. Okay, the next example I will do. I don't know whether I will have time to finish or not. In case I don't have time to finish, I will let you guys. Finish this. Okay, show that. Right. Okay. So condition 1. So it's gonna be u1 times 0 divided by 1 minus theta times 1 minus u1 times 1 minus 0, which is clearly equal to 0. All right, so it's satisfied. All right. Number 2 is C 0 comma u2. So it's going to be 0 times u2 divided by 1 minus theta, 1 minus 0, 1 minus u2. And this is 0. Right? So condition 2 is satisfied. Condition 3, C u1 comma 1. So this is going to be u1 times 1 divided by 1 minus theta, 1 minus u1, 1 minus 1. 1 minus 1 is 0, so this whole thing is 0. So this is u1. So this is satisfied. All right. Condition 4, C 1 comma u2. So this is going to be 1 times u2 divided by 1 minus theta times 1 minus 1, 1 minus u2. 1 minus 1 is 0, so this whole thing is 0. So this is equal to u2. So this is satisfied. All right, condition 5. All right, this is where you will need to use the caution rule. I'm sure you guys remember that. So you will need to find the partial derivative of c with respect to u1. You will need the caution rule. I'm sure you know how to do that. Let me see. One minus. I will do it in a short way. I mean, I will do this in a short. If you apply the caution rule, right, right, and simplify things, right, you get not simplify. Well, after u1, u2. And then there's a theta here. I'm doing it in a faster phase than usual. Normally I would do it step at a time, but because I'm running out of time, I'm doing it in a faster phase. Right, this is what you will get, I think. Correct me if I'm wrong. Now, the next step is that you will need to simplify these two guys. And I'm not sure if I have the time to do that, but you have to show that this minus this is something non-negative, right? You know what I'm saying? So you need to show that this, take away this. Let me see. Let me see if I can do it quickly. Theta 1 minus u2, theta u1, u2. Wait, I'm thinking. Just a minute. Theta u1, 1 minus u2, u2 plus negative. So then you have yeah, I think correct me if I'm wrong, but I think this will reduce to something like the following, I think. right? So this will reduce to something like this, right? And this is clearly non-negative because this is clearly non-negative because u2 is a number between 0 and 1, and this is a number, theta is a number. So this is also non-negative. So the whole thing is non-negative, right? And similarly, you can show similarly. So this is for part 6, similar to part 5, right? Okay, I skipped the details here, guys, because of the time, but I hope you can figure this out by yourself. I'm sure you guys are genius in mathematics, so you guys should know how to show this is non-negative, right? Okay, guys. So on Thursday, I'll see you guys on Thursday, and on Thursday we will go through the tutorial sheet. I'm sure you know the tutorial sheet for Thursday, right? I mean, I told you guys in the email I sent to you. So if you look at the email I sent to you a few days ago, a couple of days ago actually, I sent you an email saying that the tutorial sheet for week 9, which is the current week, right, is this one, right? Uh, so okay, it's this one. This is the tutorial sheet for Thursday. All right, so try to go through this as much as you can, right? So when I see you guys on Thursday, I will go through the ones which are difficult. Okay. Have a great evening, guys. I'll talk to you later. Once again, Happy New Year.